A model that you may use to describe some real-world phenomena may need multiple equations to describe it, sometimes infinitely many equations. Collectively, if you combine all these equations together, this is called a system. You don't usually say one equation is a system, but two or more you'd call a system. And of course, these can be not only equations, but also inequalities. Let's consider this sample problem here. Suppose the wholesale raw mixed nuts, so they don't contain any peanuts, is 32 cents per ounce. Of course, mixed nuts that don't have peanuts are typically more expensive, and the cost of wholesale peanuts is 8 cents per ounce, much cheaper. Of course, to reduce costs, you can blend the two to make somewhat a decent nut mix, but for a cheaper price, since peanuts are cheaper. If we want to sell 1 pound cans with a cost of no more than $4 for a can, how many ounces of each should we use in each can? So for a problem like this, we really need variables. You can't do much without variable. And so we ask, what do we want to know? Well, we want to know how much or how many ounces of each, the raw mixed nuts and the raw peanuts should we use. So I'm going to use the variable m to be the ounces of mixed nuts and p for the ounces of peanuts. And from here, now let's look at the information and see what we can do. Well, if m is the ounces of mixed nuts and p is the ounces of peanuts, and we want to sell 1 pound cans, well, 1 pound is the same thing as 16 ounces. So I'm going to use 16 ounces for our system, and because we have ounces of mixed and ounces of peanuts. Well, if m is the ounces of mixed nuts that we use, and p is the ounces of peanuts, if we combine those two things together, well, this must equal 16 ounces because that's what we're trying to sell. We're trying to sell 1 pound cans. So we want both of them combined to be 16 ounces. Okay, now we can look at the price. So we have 32 cents per ounce for a mixed nut. So I'm gonna write it like this. If it's 32 cents per ounce and we have m ounces, then that means we have 32 times m as a total cost of mixed nuts. Likewise, if it's 8 cents per ounce and we use p ounces, then it's going to be 8 cents times p. So that's the cost of each one of these things. Of course, if we combine the costs together, then this is going to be our total cost for the can. And we said the cost should be no more than 4. I'm going to set that equal to 4. And that is a second equation. And that's actually all we need for this system. This is a system of two equations. You typically will see it with this curly brace that covers both equations, saying that these two things are tied together and they represent one, situation, one thing that you're working on. Now, to solve this, there's actually quite a number of ways to solve these things. This is what I'm going to do. I'm going to solve this first equation for m. So I'm going to I'm going to subtract p from both sides. And that's going to give me m equals 16 minus p. And the reason why I'm doing this is because if we know what m equals, right, 16 minus p, then that means this m also equals 16 minus p. So I'm going to do what's called substitution. I'm going to plug this thing in. I'm going to substitute 16 minus p in for m. That allows me to write out this equation, 0.32 times 16 minus p plus 0.08 p equals 4. And it just so happens that this is a linear equation with one variable. And I can solve this thing by getting the variable by itself, like we've always done. So solving that, I'm going to distribute the 0.32. We need to get rid of the parentheses. Okay, let's see what 0.32 times 16 is. 512. 0.32p plus 0.08p equals 4. I can combine like terms. That's going to be minus 0.24p. And now to get p by itself, I'm going to subtract 512 to the other side of the equation. Let me move this up here so it's a little bit clearer what I'm doing. I get negative 0.24 on the left equals negative 1.12 on the right. Last step is just divide. That's going to give me p equals 1.12 divided by 0.24 says 4.66666. It just repeats 6. That's the same thing as saying, I'm going to write this as a mixed number instead, 4 2/3. I think it's a little bit clearer to say 4 2/3 since we're dealing with ounces rather than this repeating decimal. Well, if p equals 4 2/3, and we know that m equals 16 minus p, then that means m equals 16 minus 4 2/3, or in other words, 11 1/3. So our system, our solution to the system, if we want 16-ounce cans and sold at a cost of $4 per can, then we must use 4 2/3 ounce of peanuts and 11 1/3 ounce of mixed nuts. Okay, now taking this information and further, elaborating on it. So we're going to assume that the cost of roasting, canning, labor, and distribution adds, this is an important part here, adds approximately $1 per can. So this is on top of the already $4 per can that we had. So it's going to be $5 total. And we have a fixed cost of $5,500 per month. Think of this like rent, utilities, maybe the cost of, energy, whatever distribution you're trying to get in to plug in. I don't know. It could be a lot of different things. But a fixed cost of $5,500 per month. What is the break-even point if we sell each can at $8 for a can? So the break-even point is an interesting point, especially in a cost-revenue statistics. It's where the cost and the revenue are equal. That means your business is not making money, but it's also not losing money. This is a very important point to find because you know exactly how much you need to make to start making money at that point. So let's go ahead and find this. To do so, we're going to use a variable x. We only really need one variable here, as it turns out. But x is going to be, really what we're asking is, how many cans do we sell? Like how many cans do we need to sell for this situation to get a break-even point? So x is the number of cans sold. At this point, we can actually come up with the two different equations that are important for what we're trying to find. We have a cost equation and a revenue equation. A cost is pretty much what does it cost to make what you're making, and a revenue is how much money do you bring in from what you're making. You don't care about, cost doesn't care about how much you bring in, and revenue doesn't care about how much goes out for costs. It's just purely those two things. So a cost function would be, well, if we have a fixed cost per month, this is a per month cost function. That means it's going to be at least $5,500 plus however many cans we make in a month. So this should really be number of cans sold in a month, because we're always looking at this thing in a month by month basis. So if it's $5,500 for a fixed cost plus this variable cost of not $1 per can, but $4 from the previous problem is $4 the cost to make the can, plus the $1 for the roasting, canning, labor, and distribution. That means it's $5 per can. So that's going to be a cost of 5x, $5 per can. We produce X in a month. It's going to be 5x for that cost. This is our cost function. The revenue is much easier. We only bring in $8 per can. If we sell 8 cans, that means our revenue is 8x. And this is our system. So the break-even point is all we really want to know. The break-even point is simply, when does the cost equal the revenue? Well, we know what C of X is. C of X is right here. R of X is right here. This is a linear equation in one variable. We can solve it by getting X by itself. I'm going to subtract 5x to the other side. Equals 3x. And then divide by 3. So we get our x equal to, go ahead and do that. Divided by 3, it's going to be 1833.333. Repeating, of course, you can't produce 0.3 of a can. So really you should round this upward. This is really 1834. So this is our break-even point. If you were to try this whole situation out and you could not produce 1,834 cans in a month, then that means this is a failing business. Do not do this. If, however, it's quite easy to make above 1834 cans, so like for instance like 2,500 cans, then that means you're going to make a profit. And really, a profit is what you're looking for here. Profit is just a side note. Profit is revenue minus cost. If this is not positive, then you're just losing money. Break even, of course, is when this equals 0, which is the same thing as when cost equals revenue. Now, both of these situations that I've described here, I've gotten solutions for it. Here, I found what P and M are, and here I do have an answer for X. These two types of systems, or actually it's the same type of system, we have a solution that makes it a conditional system. The system is true based on the condition that, in this first one, P equals 4 2/3, M equals 11 1/3, and the second one, X equals 1834. Now, there are actually 3 types of classifications for solutions. Here we had a conditional one. There's also 2 more, just like there was in linear equations where we had conditional, inconsistent, and identity. Here we have conditional. And then here, we're going to look at this one on the left. We have 2 lines. If we were to graph these 2 things, because these are just relations, and these are actually functions more specifically, and you can graph them, and they actually are right on top of each other. They're just the same line. I just created one dotted blue so that you can see they're both the exact same line. Now, if I'm going to use the substitution method that I showed you, I'm going to take this thing, because we already know what X equals. I'm going to take this thing and plug it into the X variable in the bottom. What that gives me is 2 times X. X is just 4y plus 5 minus 8y equals 10. This is a linear equation of one variable. I can solve by distributing and getting the variable by itself. I have like terms here, 8y and negative 8y, those cancel. And we get 10 equals 10. This is a true statement. So it actually has infinite solutions. And you can see this because every point on these lines intersect. And so there are infinitely many of them, so there are infinite solutions. Of course, a point over here, this point here, this would be what, -2, 2? This is not a solution to this system. but there are infinitely many solutions. So there are still some solutions that are not true, but there are infinitely many that are true. And that's what we're talking about here. This is called a dependent system. Y depends on X. And all you have to do is really choose an X value, and you can go down to the function, and then you can find your Y value. And that is a solution. If you choose a different X value, you get a different Y value, but it's also a solution. So Y depends upon X. That's why it's called a dependent system. Now, over here, we have two lines that do not intersect. That means there are no solutions to this system because you're looking for an intersection point. And to show you this, I'm going to take this system and I'm going to solve it a different way. I'm going to solve it using what's called elimination or addition. So I'm just going to rewrite the system down here, the exact same thing. And then 6x minus 5y equals 2. And now I'm going to solve this by looking at the bottom equation. You can do either one, but I'm going to look at the bottom equation. I'm going to try and match the x coefficients. So 6 times what is 18? 6 times 3. So I'm going to multiply everything by 3. And I'm actually going to multiply everything by negative 3 so that these two numbers have the same coefficient but opposite signs. And so I'm multiplying everything in here by 3, both sides of the equation. So the top equation stays the same. The bottom equation becomes negative 18x. Negative 3 times negative 5 is plus 15y. And negative 3 times 2 is negative 6. And now I have all of my columns lined up. I have the x variable, the y variable, the equal sign, and the numbers. Everything is lined up correctly. I can add going straight down. 18x minus 18x is 0x. Negative 15y plus 15y is 0y. 19 minus 6 is 13. 0x plus 0y is just 0. 0 equals 13. No, this is a false statement, which gives us no solution. And that we knew because the two lines were parallel. Okay, this is, once again, an inconsistent system.